Swayam Prabha. Digital India. Educated India.
So I will cover a little leftover from last lecture, and I did not go through all the details. There is a lot of details in deriving those equations. They are in chapter 11. I mean, there is no reason for me to go over all the nasty details. Okay, and you also, when you read, you can read as much as you find it useful. Okay, if sometimes you might want to derive it yourself and check it for yourself, but otherwise you could take what I write, and you may also read it not just in one stretch, but over time you could read. So bottom line is that deriving the equation that you are solving, whether it's Euler-Lagrange or Euler-Euler, is a very useful, sort of a little bit of a humbling experience, because you know where those equations are coming from. Because typically in your fluids, graduate fluids course, they derive Navier-Stokes equation, so you know it. But then multiphase equations, we use it left and right, but it's an important thing for everybody who is working this to know how it is derived and how you get the version that you are using. Because since there is no single equation, you have to ask a question, so what approximations have I made in deriving those equations? So that's the reason that this lecture 11 is a useful one, but I didn't want to get bogged down in sort of mathematical detail. But having said that, you see there's a lot of equations, but I tried to keep it simple. So the question is, for Euler-Lagrange, what we discussed in the morning was enough. Now if you're going to do Euler-Euler, you say, well, I don't want to track individual particles, and therefore you have to average the particulate phase. Now in red you see indicator function is the complement of the continuous phase. If it's not continuous phase, it must be dispersed phase. And then just like you have a fluid property which will get only counted, only the fluid region will get counted. Here you have any particle property, you multiply it by where particle is, indicator function for the particulate field. And then it's the same idea, only thing is that in the notes you will find that I say average over the dispersed phase, okay, as opposed to average over the continuous phase. In particular, if you take the psi to be 1, in other words, if you integrate just the indicator function, you are averaging wherever particles are, and naturally that will give you volume fraction. Since IC and ID add up to 1, phi d and phi c will add to 1. Okay, so in other words, volume fraction of particles is 1 minus that of the fluid. And that's why I said when it is very dilute, you can take volume fraction of fluid to be 1 and don't even worry about it. In many simulations, in the previous equations I showed, I had phi c in the equations, but you can set it safely to 0 because it's almost 1. The volume effect, if it's not big, don't bother with it. So in other words, you can make the equation much simpler than what I had. Okay. Now here you can density of the particulate phase. Obviously this is in an incompressible flow. If it's a rigid particle, who cares? Only in bubbles and compressible like flows you have to worry about particulate density being average, otherwise you will say it's a constant. Okay, but then particle velocity now becomes important. Now you see in Euler-Lagrange, Euler-Euler, when you talk about particle phase velocity, you are averaging the velocity of the individual. A Lagrangian quantity has been converted into Eulerian quantity. So the previous slide was just introduction. So you take the, here you have to take Lagrangian equations of motion and you average over all the particles, And these are the kind of equations you get. So here I have assumed density of the particle to be constant, so I pulled it out. So this is the volume fraction equation. I'm pretty sure those who are using Euler equations, you solve this. And on the right hand side you have the source term. M dot from this definition is the mass going from the fluid to the particle. So M dot will be positive for condensation, M dot will be negative for evaporation, and this appears just as with a negative sign in the mass balance equation of the gas. So it's pretty straightforward. So the same averaging, swapping the integral with the derivative, Gauss rule, Leibniz rule. Those Gauss rule and Leibniz rule are very important because that's the only way you're going to get how particles and the fluid exchange mass momentum. Okay, the Gauss rule and Leibniz rule are very important. This is one way of deriving. There are other ways of deriving in a finite volume context. People like Jackson, I don't know how many of you are familiar, they derived average equations. They do a slightly different way. But I use this is the kind of way some people have solved, especially Olivier Desjardins and has a paper. Okay, filtering approach. Okay, they're motivated for LES. Okay, but the idea is the same. So what does the equation look like? So we have made sure that time derivative, the advection term, and this is the subgrid particle velocity fluctuation. In other words, ud is the particle's average velocity, but each particle there is moving little different from the average, and therefore just like Reynolds stress, you will have particle velocity based subgrid stress will appear. Okay, this accounts for the fact that particle velocities fluctuate from the average. Okay, it's not small scale eddies anymore, but the effect of the small scale eddies on the particle velocity. Okay, often this term is neglected in some. Sometimes people take care of it, but often it's neglected because we don't know a good model for it. Okay, if you don't have the model, you just throw it out. There's nothing else you can do. So this is gravity. This is basically this is nothing but the undisturbed flow force. Okay, if you look at it carefully, this is nothing but undisturbed flow force. So in other words, ambient flows, pressure gradient, and viscous stresses trying to move the particle. So this is the undisturbed flow force, and the disturbed flow force is there. This with a negative sign appears in the gas phase equation. That's the Newton's law. Okay, and this is the momentum associated with this mass. So everything is taken care of. So this is what you will get, but there is one fact that is missing for particulates. This is the analog of the pressure term in the gas phase. In the gas phase you have pressure. Why does pressure come? Molecules collide and you have pressure. Here, when you just take the particles and you average, we haven't taken care of the interparticle collisional exchanges. So you have to do some kinetic theory of gases kind of stuff, and then I just like putting a band-aid, I just add on that. Okay, later in my chapter I derive this term, but for now I didn't want to talk about collision kinetic theory, etc. And I said that let's just average the way we do for gas, but then let's accept the fact that we have neglected collisions. Collisions will add terms. Terms that did not exist in the gas phase will appear in the particulate phase when you do Euler simulation. One of them is collisional stress, and it looks like subgrid stress. You can think about it, this is not unreasonable. Even without collisions, velocity can fluctuate. Particle velocity can fluctuate for three reasons. One, if you take a volume and you take all the particles in there, each of them have some velocity, But there is also cell average ud. This is this quantity, that is the average velocity of the particle. Each particle is fluctuating, and that fluctuation, I said that there are three reasons at least I can think of. One is eddies which are inside make the particles move slightly differently, effect of turbulence. Now, the other one is close interaction between particles. It could be, you could call it pseudo turbulence. Okay? So, in other words, when one particle gets close to it, its velocity has to be different. Okay? This is what I was talking about sometime, I believe, in the morning as particle particle interaction. Okay? That may create particles to move slightly differently. And the third one is, which is also close interaction, but really close interaction, which is collision. So, particles coming and colliding, some particles. So, in other words, collision is a very big mechanism for introducing velocity fluctuation. So, fluctuation between when you go there and look at these particles and say what is your velocity, etc., they may be substantially different from ud. Okay. So, that in a way, so this term and this term are very similar. You could even combine them. Okay. So, the point is that velocity fluctuations due to collisions and due to non-collisions create velocity fluctuations and must give rise to stresses. Now, I did not write it here, but you can write the temperature equation for particles. That kinetic theory of gases people do. This is not the, there are two kinds of temperature equations people use in Euler-Euler methods. One is normal thermodynamic temperature, heat transfer, etc. The other is what is called granular temperature, because particles velocity fluctuation. So, this term and this term, the source of it, how do you model it? For classical turbulence, you have eddy viscosity and those kind of models, but here we are talking about particle velocity fluctuation. So, smart people said that, look, there is no real way of doing it, let us write an equation for it. So, they will write a granular temperature equation, which I do not have it here, it is in the book, but I just want to tell you that you may want to add one more equation to understand how particle velocity fluctuates, and that equation comes from understanding collisions and other mechanisms. Okay? So, with that I will leave there to say that these are the equations that one must solve, or people who are using Euler-Euler equations typically solve. Now, sometimes people may not solve the granular temperature equation if these fluctuating velocity and collisions are not that important. You just neglect them and just proceed. Okay. Any questions on that? Yes.
Sir, on the source term, the second term in the source term, can you explain it?
This one?
Yeah. No, the one in the like.
This one?
The second source term before f phi d, the phi d into the divergence of the velocity of the stress.
Sigma c. Left side.
Oh, this one?
Yeah.
The subscript c is
Negative sign should come, positive should come.
what is it?
Sign negative third term. Positive or negative?
It depends on the definition. The way I defined it is consistent with some other. You're right. By defining tau, you look at the definition of stress. Okay, I defined it in a way that this term comes out to be negative. Okay, I hope so, because I do make mistakes in sense that I may have. So look at that book. Okay, I hope I got it right. Okay, but you're right. It could be written either way by changing the definition. Going back to your question, sigma c is, remember, this is not d, it is c. So, if the fluid stress, divergence of fluid stress is the viscous force. I am saying this is the resolved scale viscous stress. Okay. So, in other words, you remember we have smoothened it, we use either the blue curve or the green. The stress associated with that filtered velocity is the sigma c. Divergence of it is the viscous force that appears in the Navier-Stokes equation. that multiplied by phi c goes to the fluid, multiplied by phi d goes to the particle. So, in other words, if you have a cell and you have 10% particles and 90% fluid, there is viscous stress. 90% of it goes to accelerate the fluid and 10% of it goes to accelerate the particles. So, particles, so that is what is, by the way, is the undisturbed flow force. So, in other words, we are not talking about the perturbation flow. We are saying here is the flow, macro scale flow, its stress is sigma c, part of it goes to the fluid and part of it goes to the particles, and how much, what the proportion depends on volume fraction. That is all it says. Okay. There is no modeling needed, that sigma c is what you have computed earlier, okay, in the gas phase. Okay. Okay, so, I will next tomorrow onwards, I will on tomorrow I will cover modeling some more details about Euler-Lagrange, Euler methods. Okay. So, today we have sort of derived the equation, sort of glorious Euler and Euler-Lagrange equations. I want to emphasize that because there are lots of unknown terms here, and we are just saying that, oh, this model should be there, this model is, often we do not have them or they are not important. So, the equation that you may end up solving is much simpler than these equations, but this has everything in it. So, I want to cover something a little different, perhaps appropriate for the next 20-25 minutes. I would not call it lighter subject, but something for you to think about. I want to talk something more physics, a little less math, so that we can think about Euler-Lagrange versus Euler-Euler. Okay. And in fact, I want to introduce something that is even simpler than Euler method, and I want to talk about that. Look at this. When you use Euler-Lagrange, we track particles, and it is not a space dependent variable. You index. I am tracking the ith particle, and it is only a function of time. But when you do the averaging that we talked about in the last 15 minutes, you change that ith particle's velocity kind of information, Lagrangian information, to an Eulerian information. In other words, you can pick any point and ask what is the particle velocity field at that point. What you get out of it is nothing but average velocity of all the particles that happen to be in a length scale L. Okay. So, it is an average quantity. So, this is the Eulerian field representation for the particles. You made it into a two fluid, that is why it is called a two fluid. You made the particles into a fluid, and the particle fluid and the surrounding fluid are interpenetrate. Okay. So, I want to talk a little bit about what does it mean. Okay. What is the meaning of this velocity field? So, let us take this extreme sort of example where this is actually solid rocket model. Okay. So, you have a head end of a rocket and you have body of the rocket. So, nozzle is somewhere here downstream. So, flow as the surface is burned, fluid is being ejected, and let us say there are also aluminum droplets, they come and they get ejected, they come downstream. Okay. So, there are particles, and these particles, if they are really small, they follow the fluid almost. And if I look at this volume and I ask, how are the particles moving? Let us say that is the volume of averaging, that is the fuzz out volume, let us say. So, I want to know what the average fluid velocity here and average particle velocity. Fluid velocities are all sort of nice and smooth if it is laminar flow, and then you say, okay, this is the average fluid velocity, and particle velocity also are fine, and then because the particle velocity especially look at the wall normal velocity, it may be very narrow and centered about 0. All the particles right there are almost horizontally moving, they do not have a big vertical velocity, maybe a little, some of them coming down, some of them going still up. Now, on the other hand, think of these aluminum droplets being fairly large and they get ejected. So, when you look at here, some of them are still zipping up before they turn back. Now, gas does not have a problem. Okay, I mean, I do average, and all of them roughly, that is the average fluid. Now, the actual fluid velocities are like this, some going down and some going up. Now, the average of this will be 0. So, this Eulerian field will say it is 0. But the Lagrangian, if I were to track, it is going to be big negatives and big positives, some going up. And so, what I am trying to say is that the subgrid velocity for gas depends on turbulent eddies. Okay. But subgrid particle velocity depends on the inertia of the particles. That is why people solve granular, because the particle velocity can be substantially different from the average. Okay. And that is something for you to remember. So, what does it mean when you compute Euler equation, when you solve this V? So, you need to think about what that V is. So, you can think of like an average velocity, that is the only way to think about it, but you must keep in mind that the actual particle velocities may not be close to the average. So, one of the things, this is some work I did some time ago, is to say what happens in this kind of situation if the particle velocity is unique. In other words, particles are not having different velocities, at least when they are by themselves. When can particle velocity be unique? So, in other words, I wanted to ask when the situation will be like this, when the situation will be like this. Okay. And it turns out that the answer is easy, that the Stokes number, if it is less than 1, it will be more like this. If Stokes number is greater than 1, it is going to be like this. Okay. So, we went, and I had a good postdoc, and he was very interested, and he was mathematically inclined, and he said two things. So here is the equation of motion. Equation of motion, in this case we take care of drag, quasi steady drag, added mass force, and let us say gravity. Okay. So, some version of the BBO equation. So, we say that there is I am doing Lagrangian tracking. So, the question we were asking, the way typically in math you prove uniqueness. Okay. Is there one velocity, is there two velocities, the kind of stuff. So, we said that okay, there exist two different velocity fields, when their difference will die. So, I want to skip the details, they are all in this paper by Ferry and Balachandar, it appeared in IJMF. So, let us skip the details here, and what happens is that this is the fluid time scale. So, in other words, if the compressive strain rate everywhere in the fluid, take the maximum value. So, this is the fluid time scale. So, if tau p is less than the fluid time scale, which is the Stokes number, when Stokes number is less than 1, you can say that you can guarantee. So, this is a rigorous proof that if Stokes number is less than 1, it will behave like this. Now, the Stokes number is globally defined, that means fluid time scale, the worst case fluid time scale anywhere must be still bigger than the particle time scale. If that is the case, then when you use Euler, you can be safe in saying that, yeah, I do not have this kind of crossing pattern there, all the particles are nearly going. If particles are, so the main thing is that I want to differentiate one thing. I am not saying that the particles will move lockstep, I have to be very careful. Particles may have different velocities because of turbulence or particles, interparticle interactions, collisions, etc. But this difference that you see here is nothing to do with that. It's remembering initial velocity. It's memory. The fact that it's not because of turbulence there were different velocities. It's not because particle were interacting. So when I say tau Stokes number must be less than 1, the question that I am asking is, do these particles have long memory or do they forget? Okay. The turns out the answer is, if Stokes number is less than 1, particles forget, and therefore Euler method is in good shape. If the Stokes number is very large, Euler is in little shaky things. I mean, whatever you compute is based on scenario like I show here. A Euler-Lagrange method is typically better because it's able to track the fact that your particles are remembering where they get injected and so on and so forth. This is something for you to remember. In some problems where there is a lot of memory, particles memory may be lost, the Stokes number is large, then Euler-Lagrange method may be better, because towards the end in this chapter I am moving towards trying to tell you, if you have a problem, one of the big question is, should I use Euler-Lagrange, should I use Euler-Euler, what kind of method is good for me, kind of stuff. So I was trying to come up with some simple recommendations. In that sense, you calculate the Stokes number. If the Stokes number is order 1, Euler-Euler is good. If it is really large, then Euler-Lagrange may be a better thing, because you are tracking the same cell can have different particles going in whatever way they want. You have no restrictions. You are not talking about the average. Now, one thing that I am going to now talk about, if the Stokes number is really small, you don't even need to do Euler-Euler. Okay? You can do even cheaper than that. There are methods called dusty gas approximations or equilibrium Eulerian method. That's what I want to talk about next. So let's skip this derivation. So what do I mean by that? Okay. So here is a simple problem. Okay. There is a shear flow. Y is pointing down, therefore alpha y horizontal velocity increases with depth. Yes.
The Stokes number 1 is not a clear cutoff, right? It should be like much less than 1 and much greater than 1.
It is asymptotic. So yeah, you're right. Stokes number, if you want my rule of thumb, if Stokes number is like 2, 3 large, much larger than 1, Lagrangian method will, if you can afford it, will capture the physics a lot more, because you are able to track crossing kind of particle pattern. Okay. Eulerian method is excellent around Stokes number 1, okay, because they don't cross that much, and you can use Euler method has a good merit. Now, if Stokes number is 10 to the power minus 2, say for example you are tracking sediment particles which are 100 micron in a river flow, that's so small, you don't even need Euler. You can do much cheaper than that. And that is what I wanted to bring it to your attention, that there are many different methods and you want to use the best one that is cheapest for you, for your job. Okay. So I want to, in this slide I want to tell you that there are sometimes you don't even need Euler method, because particles follow the fluid pretty much. The worst case, you can simply say V is equal to U. That means particles are just simply following the fluid. If that is the case, if you know what the velocity is, you only have to solve mass balance. You don't need to solve momentum balance in your Euler, because velocity is free. Same way temperature of the particulate field, if it's so small, it's the same as the surrounding fluid. So why solve it? So what I'm going to talk about is, when Stokes number is 10 to the minus 5, 4, something like that, don't solve anything. Just simply set your particle velocity to be the same as the fluid, particle temperature to be the same as the fluid. You just have to track volume fraction, where they accumulate and so on and so forth. Okay. But what happens if Stokes number is 0.1 or 0.2? where particles follow the fluid not perfectly. Can we do something intermediate is what I am going to talk about. Okay. So, in this particular problem, we have particles sedimenting, falling down, at the same time they are going horizontally also. So, we say Lagrangian is the perfect. I mean, in other words, tracking particles, I just said that it keeps track of everything, and we take the simplest drag law. So, there is gravity, Vs is the gravity term, and this is the x drag term and the y drag term. Okay. We just solve equation of motion, and when you solve it you get exact equations. The exact equations are written here. There are exponential terms. The exponential terms are terms that are there to match your initial velocity that you dropped it. Okay. And they die exponentially, and what is the time scale on which they die? This is tau p. I am sorry. This, in other words, particle time scale is because they quickly adjust to the surrounding flow. Okay. So, once this transient die, I want you to look at this equation. The vertical velocity of the particle is the same as the fluid. I am sorry, is the settling velocity. Okay. So, it is just falling down. Okay. Now, look at this x velocity. It is very interesting. It says x velocity of the particle is the same as the local fluid minus this term. What do you think is this term? So, in other words, particle falling down is going to faster and faster fluid, but at any point the particle's velocity is almost the same as the local fluid minus a little bit. Why? Because it came from a layer where it was slow moving fluid. So, every time a particle goes down, it sort of little bit remembers that it moved from a slow moving fluid. So, it will all, and this lag is proportional to tau p, and it is also proportional to how fast it is settling. So, somebody was this morning was talking about a particle cutting through very fast through turbulence. Okay. So, in other words, if it goes very fast, then it may cross many layers. So, its lag may be very big. Okay. The point I want you to look at this and say, why do I need to solve Euler equation? In other words, why do I need to solve momentum equation for the particle? Let us say I solve the fluid equation and I get the fluid velocity. This guy is entirely in terms of fluid velocity, u, derivative of u, that is all is needed. If I know u and derivative of u, only other thing I need to know is that what is the time constant, what is the settling velocity. These are the particle properties. So, in other words, the lesson is particle velocity can be written in terms of the local fluid velocity. So, this is what I like. It is often done, used to be done in the US, and I am pretty sure here also, buy one get one free. Okay. You buy your fluid velocity, you get your particle velocity for free. In other words, you may want to solve for fluid velocity. Once you solve your fluid velocity, we can do particle velocity. Now, yesterday somebody are talking about PIV measurements. Okay. They were asking a very interesting question. In PIV, so think of it this way. This is a equation. Let us say you are doing PIV for this problem, and you are tracking particles, and you are getting fluid velocity field in PIV. You are measuring V, not U. But once you get V, you can turn it around and say what U would give me this particle velocity. So, in other words, this equation is a great equation, provided the particle's Stokes number is not very small and not very large. Okay. Okay. So, I will go to the next lecture, and I will. Any questions on that? So, what I have tried to do here is at small but not zero Stokes numbers or small tau p's, particle velocity can be expressed in terms of the fluid velocity. That is the main take home message, or fluid velocity could be interpreted by looking at what the particle velocity is. Okay. Now, if the particles are moving ballistically, you cannot say anything about local fluid velocity in terms of particle velocity, because they are just remembering where they got injected. They are not following. That is why this velocity I will call it, when particles are in equilibrium with the surrounding fluid, particles velocity can be written in terms of entirely the fluid velocity, and that is what I want to cover, and then we will close today's discussion with that. So, I said particles are in equilibrium. What is equilibrium? Equilibrium means that the particles are their velocity is only dictated by the flow, not from where it got injected.
So, the last equation you showed, like that's valid up to order tau square.
Yeah, I will. That's right. It's an expansion, and it's accurate only to order tau. Yeah.
So, like if I take the next term, will it be much like up to what term I can neglect? Like sometimes the second term is also important in some form.
We haven't explored a whole lot. Second term may be a little bit more accurate. I can show you some results. Our work that Ferry did shows that second term is not that, it does not buy you a whole lot, okay? But maybe a systematic study may be needed. Okay. Yeah. So, this equilibrium is important because it tells you that particle velocity, I do not need to solve it fresh. It is related to, this is I am talking about reasonably small particles. They are anyway following the fluid, maybe deviating a little bit. If I can guess that deviation, why bother with computing it? Because that there is another big advantage. If you have polydisperse and you are doing Euler-Euler, you got a bin. Let us say you have 5 bins and you have 3D simulations. You have 15 equations of momentum that you are solving, x, y, z momentum for 5 different sizes. If I tell you that you do not need to do all those things, just you get your velocity for free, that can incredibly save your time. Same thing with temperature, particle temperature for all 5 sizes, but they have to be small. This also says another thing, if you have 10 different bins, 5 of them are small, 5 of them are big, do not compute the 5 small ones, you get them for free. Okay? That is the kind of thing that I wanted to talk about. So, for that, particles must be sufficiently small that their motion is dictated by the local fluid. Okay? Then field representation is possible. But one thing I want to emphasize, that this is not saying V equal to U. For very, very small, you can do that. But we are going to say that particle velocity is different from the fluid. It is because the difference comes from the fact of local acceleration. If a fluid is locally accelerating, particle is not able to follow it that closely, and that is why it is going to lag, and we can predict what that lag is. Okay. So, I will give you an expression, explicit expression in the next slide. So, here is the derivation. I am not going to worry about this. Let us skip this thing. Here is the answer. Let me go to my original. Yeah, no, that is okay. Sorry, there are circles in here. So, here there are 2 parameters. One is Stokes number, the other is settling velocity. And there are different formulas you can use depending upon whether they are very small or small. If Stokes number is 10 to the power minus 3 or 4 and settling is not that important, well, go ahead and just simply put V is equal to U, the particle velocity field. Anywhere the particle is, it just follows the local fluid. Now, number 2 is you are saying Stokes number is really small, no inertia really, but settling is not negligible. This may be important, I will tell you why. Although settling velocity and Stokes number are related, the reason I am saying is settling is persistent. even if you are going at millimeters per second, you are going the same direction constantly. It's not like turbulent flow, a little bit here, a little bit there. So the same level of velocity for a fluctuation, you would say forget it, not because it doesn't add up. But when you neglect settling velocity, you be careful in the sense that it may not be, because it's a slow acting kind of guy. Okay, so but so the main point is that in this number 2, if you model, for example, for many geophysical flows, this is a great limit. I do many simulations. Students have done that, good publications. We just use this V equal to U plus Vs, environmental flows, because there was no need for Euler-Lagrange, there was no need for Euler-Euler simulations. This was good enough. Okay. Again, the motivation for this lecture is us to think which method is good for me, kind of stuff. I mean, we don't have to use the most complicated method all the time. Yes.
Yeah, like Stokes number is defined based on settling or based on the shear?
You should do both. Okay. So in other words, the worst case Stokes number is what is important. So in other words, if there are many fluid time scales, you want to know, can I neglect the response to every one of them? So if every Stokes number is small, then you say, well, particle is ignoring every fluid variation. Okay. So it could be due to settling, it could be due to response to a shear, etc. Okay. So in other words, what we are saying is, as you will find here in the next limit, settling is not important. Some engineering problems where something happens, if spray is coming only for a second or so, is going to burn. Gravity is not that important, but Stokes number becomes important. There, settling velocity is not important, so you can do this. Now this is what, here is where the Stokes number, I mean, though it's not written in terms of Stokes number, you can see the particle is not responding to the local fluid. Du dt says here is the fluid is accelerating locally, and the particle says, I just can't follow you that closely. So it will lag. So if the fluid is accelerating, they also, it's different. The beta, I should tell you, beta is a density parameters, is 2 rho, I think rho plus 1 or something like that. Okay, I will put a question mark. Okay. So but I will tell you, beta equal to 0 is heavy fluid, I'm sorry, heavy particle. Beta equal to 1 is neutrally buoyant, and beta equal to 3 is bubble, the way it is defined. So I did not write it very well, so ignore that. So beta is just a density parameter. So you can see neutrally buoyant particle will accelerate with the fluid, heavy particle will lag, bubbles will lead. Okay, so very simple analysis. So you say, so here you don't have to solve Euler-Euler equation, you don't have to do Euler-Lagrange equation. Just from where the particle is sitting, you read your local fluid velocity, you read your local acceleration, fluid acceleration, and then you plug it into this formula. It does not matter what the size of the particle is, you get immediately the velocity. Okay. Now if both of them are small but not negligible, so you get this sum of those two. Now you can even analytically treat if settling velocity is very important. So in other words, depending upon what is important and what is not important, you can write explicit equations for particle velocity in terms of the local fluid velocity. Okay. So this is what we call equilibrium Eulerian velocity, and the same thing applies for temperature. You can say particle temperature is explicitly in terms of what the local fluid temperature and the local fluid temperatures gradient, which is available in Euler method, in any CFD it is available to you, and you do not need to compute the particles at all. Not only this, you can get the spin rates of the particle, because the particle is spinning only in response to the surrounding vorticity, and you can do the same analysis and you can find. So, essentially everything pertaining to the particles you can get from your fluid. No need to solve additional momentum energy equation, but one thing you must however solve is this equation. Maybe a diffusion term. This equation you must solve, the mass balance equation. Only thing is that now you have your V for free. The particulate velocity field, you just pick one of the things from the previous slide, okay, depending upon whether Stokes number is important, whether thing. Now, this all does not work if Stokes number is 1 or above. It is good only for small Stokes number. So, in general for Stokes number 0.1, 0.2, you may not even do Euler-Euler. If Stokes number gets closer to 1 or little more than 1, then you must do Euler-Euler. If Stokes number is really large, you could do Euler-Euler, but Euler-Lagrange may capture those variations better. Okay. With that, I am going to stop for yeah.
So, like the problem which you showed is the previous slide. So there that if it's a CR flow, like if it's a deterministic flow, that small u I know already.
Yeah, or even in any turbulent flow, you know it computationally.
But the thing is, if it's a turbulent flow, then I need to know the velocity felt at every point.
Yeah.
And that, and I need massive interpolation, right?
But that is only for Euler-Lagrange. Okay, you are right. If you have Euler-Lagrange, yeah. But what I am saying is, why do you even want to track particles? Think of it like Euler-Euler. If it is Euler-Euler, you have u at every grid point, you calculate du dt at every grid point, you have v at every grid point, and then you have to only solve this equation. You do not need to do tracking particles. I mean, of course, you can track particles and you could use this velocity, but why? Yes.
Sir, in Euler-Lagrange method also, like if we want to match the velocity field with the mean velocity field, I mean we have the experimental data of mean velocity field, and we have to match the velocity which we are getting from Euler-Lagrange with the mean profile. So, what do you think? What type of averaging will be the best to, I mean, to match those two profiles?
Okay, it's a turbulent flow, right?
Yes, sir.
Then you should do averages, because instantaneously if you measure your experiment, it's like random process and your simulation won't exactly match this. So, I would say you should do a time average of your thing, yes. Okay. And in the Euler simulation you have average over some volume. So, you should also do some time average and try to compare with your measurement. Okay. That makes sense, because instantaneous quantities are fluctuating, that they are hard. And also you can compare not just the mean, but RMS to know that if your level of fluctuation that you see in the experiments is the same as that you are computing. So, not just the mean will be sufficient, but you may want to compare the RMS whether this is good. Yeah. All right. Thank you, guys.